And let's okay, great. So today we're going to finish up what you started talking about on Friday, which is breadth first search, or BFS, specifically talking about how to reconstruct the path once you eventually find the node that you were searching for. And then we'll talk about Dijkstra's algorithm, which is it solves a really important problem with graphs, which is, okay, so we can find a path, which is depth first search. We can find the shortest path in terms of the number of edges, which is breadth first search, but can we find the least cost path in terms of edge weights? So we'll talk about Dijkstra's, and then there's another algorithm that we'll start talking about today, which is called A-star, which is basically like a new and improved version of Dijkstra, so it runs a little bit faster. Okay, so hopefully this looks somewhat familiar from Friday with breadth first search. It didn't all disappear over the weekend. But the idea behind breadth first search is you're storing all the nodes you're looking for in a queue. And then every time you see a new node, you mark it as visited, and then you look at all of its neighbors. The main difference I wanted to talk about today is if we have this queue of vertices, you're never going to be able, like, okay, so I happen to see this vertex, but that's not a good way to reconstruct this path. So in order to do that, we can keep track of the previous for each node. So, you know, A's neighbors are B, E, and D, so we would say that their previous was A, and go from there if you're trying to search from, you know, A to F or something. So that's the big difference. You will be implementing this on your homework, so I don't want to give away too many of the details about how you can keep track of this, but just think, you know, maybe how I should be keeping track of each node's previous when I'm doing this algorithm. Cool. Some good observations about breadth first search are it's always going to find the shortest number, or the shortest path in terms of number of edges, which if the graph is unweighted, it will be the optimal cost. Though, as we'll see with Dijkstra's, for weighted graphs, this might not be the least cost path. One difficulty is that it's harder to reconstruct the actual sequence of edges that you traversed in your path. So with DFS, it was really easy because we just, you know, kept track of a vector of vertices. But in BFS, you'll have to put a little bit more thought into reconstructing that path. Depth first search uses less memory because it doesn't have that whole queue, and it's a little bit easier to reconstruct the path. But BFS finds the shortest path. So there are just some trade-offs that you might want to think about if you ever are told, okay, you just need to find a path between two vertices. Okay. What questions do you all have about BFS before we move on to Dijkstra's? Okay. Oh, and one last thing. If anybody is curious, I will talk about the runtime. It's basically you travel each edge once and each vertex once. So it's O of V plus E. And we'll talk about, so one thing to notice is this is O of V plus E. We'll see that Dijkstra's has a little bit of a larger runtime, which is why we don't just always use Dijkstra's. But same runtime as DFS. Cool. Okay, so I've been alluding to this idea of having this weighted graph and how can we find the shortest cost path. So some good examples of this in the real world are sometimes, you know, instead of flying nonstop from here to New York, it might actually be cheaper to stop in Chicago or something. So if you care more about money versus length of time, like you might want to stop in Chicago and save a couple $100 on your ticket. Does anybody else have any other examples of like a real world graph where you care, where each edge has a certain weight and you might care about minimizing the length of the edge versus the number of places you visit? Yeah.
This is very similar to the airplane one, but if you're navigating city streets, you could weight each street with the amount of time it would take to traverse it instead of just its length.
Yeah, exactly. So the example is if you have a map of a city, you might want to weight each edge by the length of time that takes to traverse it, because it's very different going up doing 1 mile on the street that's in San Francisco. I don't know if you've seen pictures of it, but it looks like this because it's so steep. Like, one vertical mile of that is very different from 1 mile on a normal street, right? So you might not want to take that street if you're trying to minimize the amount of time. Great example. Does anybody else have any other ideas? Another example might be if you're like how servers handle requests. Sometimes, like depending on the latency of that server, you might want to go to more servers that have shorter latency overall, sort of thing. So that's another example. Okay. So as an example of why BFS is not a good enough solution, can anybody see what BFS from A to F would find? Which path it would find? Yeah? Yeah, A to E to F. Okay, so BFS would find this path, right? Okay, so that cost is 9. Anybody see a better path? Yeah, actually here, over there. Did you have your hand up? Okay, yeah? Yep. Okay, so A, D, G, H, F. So instead of 9, that cost is only 6. So sometimes making more stops is cheaper overall, depending on your graph. So with this graph, it's pretty easy because we can just look at it. But you can imagine with hundreds or thousands of vertices and edges, it might become a lot more difficult. So this guy, Dijkstra, came up with an algorithm that basically fixed this problem. So Dijkstra is a pretty big deal in computer science. He won the Turing Award, which is sort of like the Nobel Prize for computer science. So if you look at the list of people who've won the Turing Award, it's very impressive. My favorite, it's not true, but like my favorite anecdote about Dijkstra is you can see his name is IJK, which as this legend goes, that's why loop counters in CS start with IJK, right? It's all because of this guy. So he's very influential in computer science. So he saw this problem and developed an algorithm to find the minimum weight path or the minimum cost path between a pair of vertices in a weighted directed graph. So it solves the idea of, okay, we need to find the shortest or least cost path from a given vertex. So it's not like so this algorithm won't necessarily find the least cost path between, to find, it's good at finding A to F and A to E, but to find B to F, you'd have to run this algorithm again, sort of thing. The basic premise about it is every time we see a new vertex, we're going to compute its cost in terms of the previous vertices that we've seen. So instead of having a queue where we just blindly enqueue neighbors, we're going to keep track of the edge costs to get to those neighbors. And then as we go through this algorithm, we'll update those costs, and eventually we'll have the least cost path. Okay. So the pseudocode is a little bit more involved. The idea is basically we start at V1, A in our example, and that has a cost of 0 because we're already here. And we don't know any information about any other nodes, so we're just going to say they have an infinite cost. Then so we've seen using a queue before. We're going to use a priority queue because we want to order based on the edge costs. So we're going to use a priority queue of vertices ordered by cost. And then while the PQ is not empty, we're going to dequeue the least cost node and mark it as visited. Then we'll look at the costs to get to all the other neighbors and say, okay, so the cost to get to all of these neighbors is at most the cost it took for me to get to this node that I'm at right now, plus the edge cost to get to my neighbor. Right, so if if I'm at node B and it took 7 to get to B and there's an edge of length 2 to get to C, then the total cost to C would be at most 9. So this cost might be less than our current cost for that node. So if it's less than that current cost, then we would NQ that neighbor with the lower cost. And if it's greater than, we just ignore it, because maybe we can get to C with a cost of 8 instead of a cost of 9. So we would just let C lie with 8. And then we need to remember which vertices we had to traverse in order to make that path again. What questions do you have about this? We'll do an example too, but. Okay. So, okay. We have, so let's say we're trying to get from A to F, our favorite example. So in order to do this, we'll have a certain coloring scheme, which is that yellow means it's NQ'd. So, we start off our algorithm only NQing our start node with cost 0. And then white is nodes we know nothing about. So for all we know, like maybe there's not even a way to get to those nodes in this graph, starting from A. And then green are the nodes that we've visited and processed and DQ'd from our priority queue. Okay? So our first step is we want to get all of the neighbors of A, and we want to NQ them into our queue. Right? So does anybody know what our queue should look like after or our priority queue should look like after we've processed A? Yeah.
D1, D2.
Okay. Yep. So we have D1 and B2. Exactly. So we know that it's possible to get to B with at most cost 2 from A, because we can just travel this edge, and we know that we can get to D with at most cost 1 by just traveling this edge. Right? So we would then update both of these costs and say, okay, my previous is back to A at this point. Okay? What's the next node we're going to look at? Any ideas? Yeah, we're going to look at D because D is lower cost than B. And those are 2 things in our queue. Okay, so we'll look at D. What are the neighbors of D? Heard C, okay. F, E, and G. Okay. So what would the cost of C be, for example, that we would NQ? Okay, I heard some people say 2. Any other ideas? I'm seeing some people say 3. So you're totally right that the cost to get from D to C is 2. However, it took us 1 to even get to D, right? So since we're trying to find the distance from A to F, so we want to find the distance starting at A, the cost to get from A to C would be 3. How do people feel about that? Okay, so D would be NQ'd, or C would be NQ'd with 3. F would be NQ'd with 9, right? So 1 plus 8. And then G would be NQ'd with 5, and E would be NQ'd with 3. So 1 plus these edge costs, because the cost to get to D was 1. So, okay, so what is the next node to be DQ'd? How many people think B? How many people think, okay. How many people think C? How many people think E? How many people think G? F? What about I? Okay, not I. Yeah, so I think you all got it right that B is the next one because its current proposed cost is 2. Okay? So we look at B. So what are the neighbors of B? D and E. Do we need to do anything with D? No. So we ignore D because we visited D. What about E? What should we do about E? Like, do we want to change the priority or keep it the same? How many people think change? How many people think keep the same? Yeah, so we want to keep it the same because 2 plus 10 is 12, which is a lot bigger than 3. So the fastest way to get to E is clearly not through B. Okay. So what are we going to look at next? Well, it's actually a tie between C and E. So let's just pick C because that's the way the slides are written. So, okay. C points to H and F. H goes in with priority of what number? 16, right. 3 plus 13. What about F? How many people think we want to change the priority of F? How many people think we want to keep it the same? Okay, non-participation, it's, okay. Yeah, like elections have better turnout. You all can do better. Okay, so let's try that again. How many people think that we should change, so we're looking at C. How many people think that we should change the priority of F? Awesome. Okay, how many people think it should stay the same? Cool, great job. Yeah, so our new priority, we know that if we go through C, we can get there with a cost of 8, right? 3 plus 5, and 8 is less than 9, so that's why we want to update F. Okay? So now we're looking at E. E's neighbors are E's neighbors are G. Do we want to update G? How many people think yes? How many people think no? Okay, exactly. So, okay, we ignore updating G. The next thing to be DQ'd is H. Sorry, the next thing to be DQ'd is G. So G's neighbors are F. How many people think we should update F? How many people think we should leave it? Okay, so 5 plus 1, so F now becomes 6. Then our next thing that we DQ is F. So therefore, we found that it has priority of 6, cost 6. And that path is A to D to G to F, if we trace back the previous pointers. Yeah. How are you storing the... Mm-hmm. Okay, so the question is, how do we know that like the previous pointers are, F's previous is G and G's previous is D, etc. So this is a question you'll have to think about on your homework. You should store them because otherwise that step isn't possible. And there are lots of different ways to do it, so just be creative. Yeah. Sorry, I'm having a hard time hearing you. Yeah, so the question is, you're doing is you say, like, I don't care how I got to where I currently am, but I know that that cost is like 7, let's say. And that might be the cost of traversing 3 edges or 10 edges or however many edges. But the cost to get here was 7. So if I have an edge, so if I'm looking at my neighbor and that has an edge weight, the cost to get there would be 7 plus that edge weight. At most. And there might be a faster way to get there, which we saw as we were going through that example, where we don't necessarily always want to have these priorities. Yeah, so the question is, like, every time you see a new neighbor, you're adding all the costs plus that new neighbor. And yes, you want to keep track of, like, the entire cost to get to where we currently are. Yeah.
Would you represent, like, the number of the node as, like, infinity?
Yep.
When we're actually programming that, like, you know, we can't just put, like, an infinity, but, like, how would we represent that? Just, like, the highest possible integer or something? Or?
Yeah, so the question is, like, okay, we're using infinity. Infinity doesn't really exist in a computer program. Like, computers don't like infinity. So how would we represent that? In C++, actually in every programming language, there's this concept of, like, the maximum int and the minimum int. So minimum int is, like, the lowest negative integer value, and the maximum int is the highest integer value. So there are constants that represent, basically. I mean, it's not positive infinity. It's something like 2 billion, but that's generally how computer scientists represent infinity. Yeah. Mm-hmm. Yeah, so the question was, okay, so our pseudocode said while the PQ is not empty. So this pseudocode finds, or like, so why did we stop when we found F instead of keep going? So this pseudocode would find the shortest path from A to every single vertex in the graph. But at this point, now that we've found F, we know that there won't be a shorter path, because like if we were to go through if there were a shorter path, assuming that all your edge weights are non-negative, like you'd have to go through additional edges, and so those edges can only add to the costs, right? So we know that there can't be any faster path to F. So this is an optimization we can make because we knew we were specifically going from A to F instead of like just find the shortest path or the least cost path from A to every other vertex in the graph. Cool. Great catch. What other questions do you all have about Dijkstra's? So a couple of just comments on Dijkstra's algorithm. It's something that's called a greedy algorithm, which is an algorithm that makes local optimal choices in the hopes that that leads to a global optimal. So specifically, we're taking what seems to be the best, we're looking at each vertex and saying that the one with the smallest cost is the one that we should look at next. And so then we're hoping that that overall leads to like finding the shortest paths overall, right? So that's an example of a greedy algorithm. If you're interested in greedy algorithms, you should take CS 161 because they talk about those a lot. It also, so this might seem like, okay, we just did this. It did find a shortest path. Maybe that was just luck. Maybe I created this example in such a way where it just worked. But it works because it always maintains two properties about your priority queue. So for every vertex that we've visited, the current, or that we've marked as in our PQ, the current recorded cost is the lowest cost for that vertex from the source vertex. So once we've visited and dequeued a node from our priority queue, there can't be a faster way to get to that node. Because anything faster would involve like all the other costs in the priority queue are greater than that cost of that visited node. So like going through any other node would be a greater cost, right? And then for all of the unvisited vertices, the ones that are still in the priority queue, those priorities in the priority queue, like those costs that we've tentatively assigned, that's the current shortest path if you only look at vertices that we've actually visited. So it kind of maintains those two properties. And that's why this works. This is why Dijkstra is a really cool guy, because he figured all this out. Okay. So, okay. Why don't you try doing Dijkstra's with a partner with this graph and see how it goes? Sorry. What did you say? Yeah. Okay, so let's go through how Dijkstra's algorithm would handle this graph. So what is originally in our PQ when we start the algorithm? Which vertex starts off in our PQ? Yeah. Yep, E0. So we always just start off with the starting node with priority of 0. So, okay. So then we're going to DQ it, and we're going to say, okay, this one's visited. So it's DQ'd. What are its neighbors? B and G, yeah. So B goes in with priority what? 80. All right, so this edge here. And then G goes in with priority of 30. Okay, so which one do we DQ? G, because G has lower cost. Okay, so we'll DQ G. Okay, so what do we NQ after looking at G? D with one. Oh, so what's the weight for one D? Wait, sorry, I couldn't hear that. So D gets NQ'd with priority what? Yeah, so D gets NQ'd with 150 because it took 30 to get to G, and then G saying, okay, it takes another 120 to get from G to D. So then that's a total cost of 150. Okay, so we'll say this one's 0, this one's 30. So okay, so what do we DQ next? How many people think we DQ B next? How many people think we DQ G next? How many? Oh, sorry. Totally didn't see A. Yes, so, okay, what do we NQ? Sorry, we're still looking at G. So what would we NQ A with? Yeah, 50. 30 plus 20. Okay, so which one are we doing next? Okay, so we visit A, DQ it. Okay, what costs do we want to, what nodes do we want to NQ? Yeah, so okay, so A had cost 50, so we can update B to be cost 70 because 70 is less than 80. So we'll change this and say it's 70. Okay, any other nodes we want to look at from A? D with cost 130. Sorry, we've already queued D, 130. Okay. So which node are we looking at next? B with cost 70. Okay. So from B, what nodes will we look at? Yes, F. So that F would have cost 80. Okay. So then can you all see the green okay? Okay. How is this? Better? Okay. So here, D currently is in with 130. F. This looks a lot better on my screen. 80. Okay, and these have cost 0, 30, 50, and 70. Okay. So which node do we visit now? Did I say that again? Yep, so D has cost 130. So I think I didn't write down F. So F has cost 80. We've done. Okay, so then D has cost 120 because 80 to 40. Any other nodes we need to add to our priority queue? C with cost what? So D has cost 120. So C has cost what? Yep, 130. Okay. So what do we DQ now? Yeah. Yeah, okay, so, sorry, backing up, hold on. I don't know if I can erase. Apparently I can't erase. Okay, so from F, we were at 80. So F would NQ C with priority 150, and NQ D with priority 120. And then we would DQ D because 120 is less than 150. Yeah, exactly. So okay? And so we'd update C to be 130 because once we look at D, 120 plus 10 is 130, which is less than 150. Yeah.
When we were at B, we just looked at F, but like, wouldn't we need to look at A as well?
So question is when we were at B. Okay, I'll answer it anyway for people who probably have the same question. So the question is, okay, we were at B, and there was a path from B to A that cost 20. So shouldn't we have looked back at A? And the answer to that is you don't want to look back at A because we've already visited A. So, and you can see like 70 plus 20 is 90, and 90 is greater than 50, which is good. Like Dijkstra's is working. So, okay. D is 120, so then C would be 130, right? And then H would be 150. How do people feel about this example? What questions do you have about Dijkstra's in general? Yeah. if you go to B and all B's neighbors cost more than G, what would you do? So then all the nodes are going to be in your priority queue. So you're always good, like, if B's neighbors cost less than G, then yeah, you might be looking like 2 or 3 or 4 hops away. So if you know the cost to get from E to G is 100, and the cost for I don't know, like 1,000 or something, you might like not look at G for a long time until you find a different path of G. So it's very possible that you could go like multiple hops out. Which is why Dijkstra doesn't find the shortest path in terms of number of edges, it just finds the least cost. So that's a really nuanced one. Yeah. Cool. Great question. Yeah.
So how is it keeping track of, for the end result, I understand how it finds the lowest cost, but how is it keeping track of like the path?
Yeah, so the question is how are we keeping track of the path? Basically, we would have to have some sort of way to store, like to associate each node with like the previous vertex that got it to that cost. So for example, when we were looking at, when we were processing E, we would have to mark for B and G that we like traveled, you know, we're NQing them with 70, and that cost comes from they previously were at E. Yeah, so you have to come up with some, it's a lot like BFS where you have to come up with some way to keep track of like, okay, I'm NQing this because of this previous vertex. Cool. Yeah. Yeah, so the question is, would it be correct to say that the priority queue has the least cost that we know of at that time? Yes. So that's 100%. That's a really good way to think about it. So only looking at vertices that we visited, so like DQ'd from the priority queue, all of the costs in the priority queue are accurate for those, like if you were to make a path only using those visited vertices. Exactly. Cool. Okay. Yes. Yes, that's a question you'll have to think about for your homework. Sorry, good try. Okay. What? Yeah. Oh, yeah, so the answer in this case, so we went from like E to G to A to, I think it's B to F to D to C to H, which has cost C, or which is path C, and has cost 150. Okay. Cool. Okay. So remember when I was talking about BFS and DFS? Does anybody remember what that runtime was? Yeah, O of V plus E, because we looked at each vertex once and each edge once. Dijkstra's is a little bit different. So the way priority queues work, since I know that you have all been working on your priority queue, you've probably noticed that the best that we could do is have an NQ and DQ and change priority of log n, right? And so your heap priority queue had that runtime. There's no way to do those in constant time, like to do all those operations in constant time. So basically every time you have to update the priority queue, that's a log V operation instead of an O of 1 operation, which is why you get into like O of V log V plus O of E log V, which, assuming that your graph is connected, that means that every vertex would have at least one edge coming from it. You can write that as O of E log V. Yeah.
Where is the E log V step in the
So it has to do with every time you're like at a current node, you're looking at all the edges of that node, right? And so then for every edge, you end up looking at the priority queue, and you might have to change the priorities, like every time you look at an edge. So and changing a priority is a log V operation because your priority queue has size V. Great question. Yeah. if you're interested in all of this, like 161 is a great class to take. They go over graph algorithms and Big O in great detail. But the point of this slide is that basically Dijkstra's is a really good algorithm for the problem that it solves, but if you're just trying to find a path between two nodes, it's better to use BFS or DFS because it has a faster runtime. Okay, so let's talk about A star, which is like Dijkstra's plus plus. So let's say we were trying to find a path from A to C, and let's say this is, some pit of despair that you can't go through, right? So if we were, does anybody have any ideas of what Dijkstra's algorithm will look like? Dijkstra's algorithm, if it could, it would just ideally go here, but it doesn't know to do that, right? So basically what happens is you end up with it will explore all over here and up here and over here before it gets to C, right? Because it's going to branch out in all directions. It doesn't know that hey, my target's over here, so I should maybe try to move this way. So the problem with this is that the only information we're taking into account with Dijkstra's is the known distance from the starting vertex to the current vertex we're at, right? So we know the distance from A to B. We were just doing that. Those were the costs we were keeping track of. If Dijkstra's were smart enough, you could have it taken a distance, you could have it maybe try to guess the distance from B to C based on some sort of heuristic. Okay? So, if we're trying to get from, here to here, we actually end up going backwards, which isn't good. And you can also see this here. So if we were to try to go from make sure this is on Dijkstra. This is what your next homework looks like. So if we're trying to go from here to here, see how it's going way up into the corner? There's just no way that's going to be the fastest path, right? We're all the way, over here and over here. That was a lot of extra work, right? So the idea is, okay, let's try to give the algorithm some hint about this unknown distance from B to C, and maybe that can let us make some more intelligent decisions than just blindly walking in every direction. So in order to do this, we're going to use something called a heuristic, which basically is a metric that's a guess for some unknown distance. So obviously, if we knew the distance, we could just use that, but that's what we're trying to solve. So that's not a great solution. So this, essentially, it's just trying to come up with a pretty accurate guess. And what's important about these heuristics is they need to always underestimate the cost, or be exact. It can't ever overestimate the cost. So a good example would be if you're trying to, if you're implementing Google Maps and you're trying to find the least cost path from San Francisco to New York, well, you know that the absolute shortest path is going to be the actual, straight line distance from San Francisco to New York, because there's not any faster way to do it than going in a straight line, right? So that would be one example of a heuristic. They actually use heuristics in other things too, there are heuristics to try to predict if a given piece of email is spam or not, and that might look at the sender, the number of recipients, keywords, if it includes the words Nigerian prince, probably spam, right? So that is an example of a heuristic used elsewhere in computer science, but for A star, we need to come up with a heuristic to guess distance. And then you'll hear the phrase admissible heuristic, super fancy term. All that means is that we can never overestimate the distance, because if we overestimate the distance, then we can get into a case where we're wrong about our, we're going in the wrong direction, right? We pick a less optimal path. So basically how A star works is the whole A to B thing is exactly the same as Dijkstra's, but going from B to C uses this extra heuristic. So you want to factor both into our priorities because we want to look at the nodes that we think have a shorter distance to our target before we look at the nodes that have a bigger distance to our target, right? Like we don't want to walk backwards to go somewhere. Okay. What questions do you have about like this concept? Yeah. Okay, that's a great question. So like, how do you pick a heuristic? Basically, you have to know something about your graph in order to pick a heuristic. Because if you don't know anything, it's very difficult to, like, you can't make a heuristic. It relies on some sort of information. So with the Google Maps example, we knew that like you can't go between two places any faster than a straight line distance. But if we are instead mapping Wikipedia, like that doesn't work because you don't have this concept of like a straight line. So it really depends on getting information about your graph and knowing something about your graph. Cool. So as an example of trying to come up with a heuristic, what do you think would be a good heuristic for this graph? Where, you know, traveling to a square, you can only travel, you know, this way or like in this direction or this direction. You can't do diagonals. Yeah.
If we knew the coordinates of each square in the grid, we could like add in the distance formula between the two spots and try and take the minimum version of that.
Yeah, so one suggestion is, okay, like we could use, it's called Euclidean distance. This is a thing you learned in geometry probably, where it's like square root of x minus, you know, x1 minus x2 plus, I don't know if you've all seen that, but, you know, basically like if you were to draw a straight line distance. So yeah, we can totally do that. That formula is a little bit tricky to remember. Is there a simpler heuristic that we could use? Like what is the minimum, like if I'm here and I want to get here, what's the minimum number of squares I need to walk? Would somebody say something? It sounded right. I just couldn't hear it quite. In the back, are you raising your hand? Okay. Like, yeah. Yep, exactly. So like if we're here and we need to get here, we could just say, okay, we have to like at least we're gonna have to walk all the way this way and all the way this way because we can't do any diagonals. Euclidean distance would also work, so that's the straight line distance, but this is just a little bit easier to implement. Specifically, it makes this slide look a lot better because I don't have to do all the straight line distances. So yeah, we would say, in this case, it would take 6 to get to C from here because you'd have to walk 2 this way and 4 this way. Cool. Okay, so really quickly, basically, so this is Dijkstra's code. This is A star. Dijkstra is A star. You aren't changing a whole lot. The big differences are where you see cost and priorities before, you would now have to incorporate that heuristic. So, we're going to have cost plus heuristic. Before we were storing the original node priority 0. Now we're going to store the heuristic. And then when we're NQing, we need to incorporate the heuristic to get from that node to the end goal. Great. Thank you so much, and have a great day.